Okay, so I'm going to explain why aldehydes are easier to oxidize than ketones, and we're comparing acetaldehyde and acetone. And acetaldehyde is also known as ethanol with an AL ending, and it's a 2-carbon aldehyde. If you compare that to acetone, which is also known as propanone, and the one ending is the ketone. So really the presence of this hydrogen is going to make it easier to oxidize because an aldehyde is oxidized to a carboxylic acid. So we're really just replacing the hydrogen with an OH group, and this will give us propanoic acid. If we compare that to the oxidation of a ketone, it's going to be more difficult. We need a strong oxidizing agent like potassium permanganate along with hydroxide. And this is going to break a carbon-carbon bond, which is kind of frowned upon. And we're going to go from 3 carbons to 2. So we're really changing the structure of the entire molecule as opposed to just adding an OH group from a hydrogen. With the ketone, we're going from 3 carbons to 2. And it's much easier to remove an R group than it is a hydrogen, or to convert a hydrogen to an OH group. We can't really do anything with an R group other than break the carbon-carbon bond. And in the presence of potassium permanganate, it's going to oxidize the hydrogens on the carbon adjacent to the carbonyl. And we have 3 hydrogens on each of those carbons. So any one of those hydrogens on those carbons can be oxidized. But as a result, we're going to get 2 products. The first is a 2-carbon carboxylic acid. And then we start with 3 carbons, so we still need another carboxylic acid, which is going to be formic acid or methanoic acid. But it's really just the presence of the hydrogen which is going to make it easier to oxidize to a carboxylic acid, because we can avoid breaking the carbon-carbon bond of the ketone.